This unit is about the photometric image formation process. So far we have discussed how individual light rays travel through space, but it's also important how actually the light changes once it reaches the sensor plane. So now we discuss how an image is formed in terms of pixel intensities and colors. If we take a picture of a scene, we observe a light field from a very specific vantage point, which is the viewpoint of the camera. And that light field is a consequence of light traveling through the scene, light that has been emitted by some light source, a light bulb or the sun, traveling through the scene, hitting surfaces, reflecting or refracting from these surfaces, and at some point reaching the sensor plane. In order to model the process of how light reflects from a surface, the rendering equation is used as a mathematical tool to define this process precisely. And this is one of the most basic equations that you will learn about when you take a computer graphics course. To understand the very basics of this equation, let P be a 3D surface point here. Let's assume this is a surface, and let V be the viewing direction and R the incoming light direction. So we have an incoming light here in yellow and the viewing direction in blue. And furthermore, we have the normal here with N at that surface point P. The rendering equation then describes how much of the light that's coming in at this point here, that's arriving at this point with a particular wavelength lambda, is reflected into the viewing direction. And in order to measure, because the light that is coming in here is reflecting into multiple directions, we have to consider the light that's arriving at this point from all possible directions on the hemisphere where the light could potentially enter the scene and arrive at this particular surface point. So what we have here is this upper unit hemisphere sigma, and what we are doing is we are gonna, this is the L out, is the light that's going out in this direction at surface point P into direction V with a wavelength lambda. All of these functions here are conditioned on this wavelength lambda because this equation is true for all wavelengths basically. So for all of these wavelengths, we are integrating over this hemisphere sigma, and we're integrating the so-called bidirectional reflectance distribution function, which determines how much light is reflected at point P for a given incoming light direction R and a given outgoing light direction V and a given wavelength lambda. So we're integrating how much light is arriving here over all the incoming light directions, multiplying this bidirectional reflectance distribution function with the corresponding the intensity of the incoming light at point P from direction R with wavelength lambda. And in addition, there is this factor here on the right, which is the inner product between the normal and this incoming ray direction, which models the foreshortening effects. You can imagine that if you shine light at a surface at a very shallow angle, at a particular point there is less light reflected because the light arrives at a very shallow angle. If it arrives exactly perpendicular, there is no light reflected. And this is what this term here, this shading term here models. Or this attenuation term here actually models. Yeah. And then there's an additional term here which is only present if this point also emits light. So there could be a light source that's reflecting light arriving from some other light source, but also emitting light into a particular direction. And so we have to add this emission term here as well for emitting light sources. Now, how do these bidirectional reflectance distribution functions look like? Well, typically they have a diffuse and a specular component, which is familiar to you. If you look at surfaces, some of the surfaces are rather diffuse and some of them are more shiny, mirror-like. And so this is illustrated here. If you have just a purely diffuse surface, that means that an incoming light ray is reflected into all directions equally strongly. But if you have a specular surface, think about a metallic or a plastic object, then there's more light reflected into the direction that is the optimal or the ideal mirror reflection here. Right? So this is the strongest effect here is in the direction of the ideal mirror reflection, and then it attenuates, it falls off if you go further away. And so here on the right we have the perfect mirror situation where incoming light is exactly mirrored away into one particular direction. So this is the whole spectrum of possible reflectance that we have, and typically surfaces or real surfaces are a combination of all of these effects. So the diffuse, the constant component scatters light uniformly in all directions, and this leads to shading that are smooth variations of intensity with respect to the surface normal. And the specular component depends strongly on the outgoing light direction. So here's a simple example with a sphere. We have a sphere of a diffuse material that's reflecting light diffusely, but you can see that depending on the surface orientation, we have a darker color or a brighter color. Here we have a specular component that is reflecting in the perfect mirror direction more than in other directions. And then here we have a combination of these two, which is the ultimate material that we might consider here. And BRDFs can actually be quite complex. So this was a homogeneous BRDF over the entire object, but in practice, BRDFs are spatially varying. Every surface point might have a slightly different BRDF, and BRDFs themselves might have very challenging aspects to them, very challenging reflectance properties, very challenging distributions. And there's a whole field about how to estimate these BRDFs and how to get good models for them. Here's another example for how challenging BRDFs can be. This is the so-called Fresnel Effect. If you take a picture of a lake or water, as here, the amount of light that's reflected from a surface depends on the viewing angle. You can see that if you look further away, you have almost perfect mirror reflection, but if you look closer at a steeper angle with respect to the surface normal, you see through that surface. And so the reflectance model has also to take into account these type of effects. Now, light does not only bounce from surfaces once, but it actually bounces from one surface and might reach not directly the camera, but might reach another surface. And it's important to model these effects, and that's called global illumination in computer graphics. And here's an example. So here's a light coming from this direction, and this is a rendering without global illumination, which looks quite unnatural. And here on the right, we have the same rendering now with global illumination, where this light that's entering the scene here is reflected from this wall and reflected from the ground, and maybe reflected another time from this wall, and illuminating parts of the scene that are not directly illuminated by the emitting light source. So this was a very short excursion on light and reflectance. Now let's turn back to cameras. We have discussed the pinhole camera model, which is actually a good approximation also for real cameras with lenses. But why do cameras actually not have just a single pinhole, but do have a lens system? Well, here we see an example from Paul Debevec, who used a DSLR camera and put a perfect pinhole, or created a little pinhole and replaced the lens with that pinhole and took a picture, and that you can see here. As you can see from the picture, it's very difficult to get a picture sharp and of high quality. And the reason for this is that there's a trade-off here. If you make the pinhole very small, then you need extremely long shutter times, which lead to motion blur or camera shake blur. But if you make the pinhole slightly larger, then you're averaging multiple light rays, leading to blur. If you make the pinhole extremely small, you also get a blur effect, but that time through diffraction at the surface of this, or close to this pinhole. And here's an example of this. Here's an example for a small pinhole that leads to a sharp projection. If I increase the pinhole size, then I get a blurry projection, because now there is multiple rays that are passing through this, but there's multiple rays for one single point that pass through this pinhole at different locations and that capture the scene, that sample the scene at different locations. And so I get an average here. And the same holds true for this point here, which is just an average of these points. And so we're getting this blurring effect. So this happens when the pinhole is very large. And if I start decreasing the pinhole, I have to increase the shutter time because the light arriving at the sensor becomes less and less. And if I'm decreasing it even further, then it doesn't become sharp anymore because of the refraction effects at the pinhole, and I get again a blurry image. So that's the reason why we want to have optics, right? So on the left is an ideal pinhole model, on the right is a camera with a lens. Cameras use one or multiple lenses to accumulate light on the sensor plane to make the picture brighter, to create more photons on the sensor plane. But there's a trade-off now, because only points that are in focus of the lens arrive at the same 2D pixel locations. And if the lens is out of focus, then you also get blur on the image plane. The good thing about this is that for many applications, it's sufficient to model the lens cameras with a pinhole model, with the simple model that we've discussed in the previous unit. And that's great. But to address focus and vignetting and aberration and all these kinds of photometric effects, we need to actually model the lens more precisely. So the most basic lens model that we can consider is the so-called fin lens model with a spherical lens, meaning that we have this lens here with a shape of a sphere on either side that is often used as an approximation for more complex lens systems. The properties of such a lens is that this lens has a focal point on either side, and that axis parallel rays pass through the focal point on the other side, and that rays via the center keep their direction. So here we have a ray from a 3D point passing through the center, keeping its direction. Here we have a ray that's parallel to the principal axis, and that is then refracted in that lens in the direction of the focal point and passes through the focal point. So all the rays that pass through the focal points and through the lens are then turned parallel to the principal axis. And the same holds true for the other direction as well. Here we have a ray that passes through the focal point and that's turned parallel to this axis here. Now, what can we do with these properties? Well, we can again use the principle of equal triangles to derive a relationship that's one of the most important lens relationships that we know. And this is the following. Here we have the red triangle relationship and the green triangles relationship. Let's consider the green triangle first. So here we have, now let's consider the red triangles first. So here we have xs over xc. So we have this distance, and xc is this distance, which is the same as this distance here. So this divided by this must obviously be this distance divided by this distance. So xs minus f divided by f. And similarly, xs divided by xc by this distance here must be the same as cs divided by cc. So this is the relationship that's coming from the green triangle. So if you have these two relationships, then we can substitute one into the other, and we arrive finally at this equation: 1 over cs plus 1 over cc equals 1 over f. So for a particular lens with a particular lens focal point f, we can determine for a particular 3D point, for a particular distance to a 3D point, how far the distance of the image plane must be in order for this point to project sharply onto that image plane. Or in other words, for a particular 3D point and a particular distance to the image plane, we can determine how we have to change the focal length or the lens system such that the point appears sharply. So here's another illustration of this. The image here on the left is in focus, here in this case here, if this relationship holds, where f is the focal length of the lens. And for this distance of the 3D point towards infinity, we obtain, in this expression here, we obtain CS equal f. So lens with focal length f is approximately a pinhole at distance f. If the image plane is out of focus, this is the example here, a 3D point projects not to a single point. For example, this 3D point here doesn't project to a single point, but it projects to a so-called circle of confusion. We get a little disk on the image plane, and if this disk is larger than the pixel size, we see blur in the image. And the size of this circle of confusion is of course determined by the distance of the image plane to the lens and the focal length and the distance of the 3D point. And that's why we have to always make sure that our lens is in focus. Another way to control the size of the circle of confusion is of course to change the lens aperture, and that's why almost all lenses have an aperture that you can set. So here you see a 50mm lens of a DSLR with the aperture, which is just basically a plane with a hole, fully open. This is an aperture of 1.4, and here we have the aperture of 8.0, which is pretty much closed. So if you close the aperture, then of course you limit the circle of confusion here by limiting the size or the circle where the ray can actually pass through, but you also let less photons pass and you need longer shutter times. So the aperture limits the amount of light that can reach the image plane, and smaller apertures lead to sharper but more noisy images. If you have ever worked with manual photography, you have seen lenses like this where there is a depth of field indicator. So the range where the image appears sharply is called the depth of field, and the lens tells you where the image appears sharply. So if you have an aperture of 8, then you know that if you focus at 10 meters, in this case here, that your range where the image will appear sharply is from 5 meters to infinity, roughly. And this is an example for a Taylor lens here on the right. Now, the aperture in typical DSLR cameras is indicated by a so-called f number on the lens. And the f number is simply defined as the lens focal length divided by the aperture diameter. So if you have an aperture diameter that's very small, d is very small, then you get an f number that is very large. So if the f number is very large, let's say 16, then you have a very large depth of field. But if you make the aperture large, let's say 2.8, then the depth of field is very shallow. You get this depth of field effect. And this is indicated here. So here we have the same image pictured with 3 different apertures, 1.4, 4, and 22, and you can see how you get different depth of field effects. Here everything is sharp, here the background is not sharp, and here only one of these blocks is sharp. So decreasing the aperture diameter or increasing the f number increases the depth of field. Another effect that plays a role is chromatic aberration. The index of refraction for glass, how lenses bend rays, slightly varies as a function of the wavelength. And therefore, different colors are refracted into different directions. And therefore, simple lenses suffer from chromatic aberration, which is the tendency for light of different colors to focus at slightly different distances. And so we obtain blur and color shift effects. So for instance, for this 3D point here, we obtain a blur effect because, as you can see here, the red colors are focused after the image plane and the blue colors are focused in front of the image plane. And so we have a little circle of confusion for both colors here. For this point here, we have an effect of blur and color shift because neither of these red and blue wavelengths is focused on the image plane, and both of them are actually focused or arrive at the image plane with a circle of confusion, but at different locations on the image plane. And this color shift is something that you can actually observe when you look closely onto images that you have taken, in particular in the border regions of wide-angle lens images. To reduce chromatic aberration and other kinds of effects, most photographic lenses are compound lenses made of different glass elements with different coatings that try to eliminate this effect. And you can see, so here on the left, you can see the effect of refraction, that light that comes in is reflected into different directions for different colors. And you can see on the right a high quality lens compared to a low quality lens, where you can clearly see the color shift and the blurring that occurs due to this simple lens that was used. Another effect that's visible for many images that you're looking at is so-called vignetting. Vignetting is the tendency for the brightness to fall off towards the image edge. And I'm going to show an image on the next slide. Vignetting is the composition of two effects. There's natural and mechanical vignetting. Natural vignetting is the foreshortening of object surfaces and lens aperture. And mechanical vignetting is the shade is due to the shaded part of the beam sometimes never reaching the image. And with shaded, I mean here the shaded part in this image. So if you look at this beam here, and these rays that pass through this part of the first lens surface, this is a multi-lens system, they actually never reach the second lens or the image plane. And this is the reason why, in particular, regions at the boundary of the image appear darker than in the center of the image. And that's called vignetting. Now, the good thing about vignetting is that vignetting can be calibrated, it can be undone, at least mechanical vignetting. And that's what's also often used. So here you can see an example. On the right, you can see the original image, which shows vignetting, and on the left, you can see the image where the vignetting was undone.